Okay, let's dive right in. We are about to tackle one of the deepest, most mind blowing questions in all of science. Seriously. It's a mystery that sits at the very heart of reality itself, a riddle that forced us to completely tear up the old rulebook of the universe and start over.
I mean, just think about that for a second. What if every single thing, the light from your screen, the electrons that power your computer, what if even you aren't just one thing or the other, but somehow both at the exact same time? This isn't just some late night philosophical question, it's a very real puzzle that physicists have been wrestling with for over a century. All right, so every good mystery needs a starting point. Our detective story begins at what you could call the crime scene of quantum physics. It's an experiment that is so deceptively simple yet so unbelievably profound that it just completely shattered everything we thought we knew about how the world works. I'm talking, of course, about the famous double-slit experiment. And the setup is, well, it's almost laughably simple. You've got a source that shoots things, a wall with two little slits in it, and a screen behind that to see where the things land. That's it. That's the whole setup. And yet, this elegant little device is responsible for one of the biggest revolutions in the history of science. So let's think about what we'd expect to happen, using common sense. If you fire little solid objects, like, say, tiny grains of sand, through the slits, you'd expect to see two distinct lines on the screen, right? One line behind each slit. Makes sense. But if you send waves through, like ripples in a pond, you get something totally different. The waves pass through both slits at once and interfere with each other, creating this striped pattern of bright and dark bands. So you have two completely different, predictable outcomes. But here's the kicker. This is where our detective story gets really, really weird. What happens if you take something we know is a particle, a single, indivisible electron, and you fire them through the slits, one by one, so slowly that there's no way they could be bumping into each other? What do you think happens then? This is what happens, and it's impossible. Each electron hits the screen as a single tiny dot. It behaves exactly like a particle. But as more and more of them land, one after the other, they start to form that striped interference pattern, a pattern that only waves should make. How? How does a single electron, flying all by itself, have any idea where the other electrons are going to land to form this pattern? It's as if each electron went through both slits at once and interfered with itself. As you can imagine, this result just blew people's minds. It's like finding completely contradictory evidence at a crime scene. Is an electron a wave, or is it a particle? It seems to be screaming that it's both. So let's look at the conflicting testimonies. You know, in our everyday world, these two things are polar opposites. A particle, like a baseball, is located right here. A wave, like a sound wave, is spread out all over the place. An object simply cannot be localized and spread out at the same time. And yet, the evidence from the quantum world was forcing us to accept that somehow it was. So let's look at Exhibit A for the particle argument, the photoelectric effect. Einstein figured this one out. When you shine light on a piece of metal, it can knock electrons loose. But here's the weird part. It's the color of the light, its frequency, that determines the energy of the electron kicked out, not how bright the light is. This only makes sense if light energy isn't a continuous wave, but actually arrives in little, distinct packets of energy, particles called photons. Case closed for particles, right? Well, not so fast, because in 1924, a guy named Louis de Broglie came along with this absolutely wild idea. He said, what if it's not just light? What if everything, every electron, every atom, you, me, this desk, also has a wave nature? It sounded crazy, but just a few years later, it was proven. An experiment showed that when you fire a beam of electrons at a crystal, they create an interference pattern. They behaved exactly like a wave. So we're stuck. We have rock-solid experiments proving things are particles, and we have other rock-solid experiments proving those same things are waves. It's a full-blown paradox. To solve it, we needed a brilliant new detective on the scene, a whole new theory called quantum mechanics, which cracked the case with a very, very strange new idea. And this is the absolute key to the whole mystery. Quantum mechanics resolves this fight by changing what the wave actually is. As one source puts it, the wave simply describes the probability of detecting the particle here or there, but never here and there at the same time. In other words, the wave isn't a physical thing. It's what we call a probability wave. Think of it as a wave of possibility. It's not made of stuff, it's made of pure information.
It basically maps out all the potential places the particle could be. The high points of the wave are where you're most likely to find the particle if you look for it, and the low points are where you're least likely to find it. So let's go back to our crime scene one last time with this new clue. Okay, step 1. A single electron, a particle, is fired. Step 2. Its probability wave moves forward, and since it's a wave, it passes through both slits at once. Step 3. Those two new probability waves interfere with each other, creating a pattern of high and low probability zones. And finally, step 4. The actual electron lands in one specific spot on the screen, like a particle, but its final location is guided by that interference pattern. It's much more likely to land where the probability is high. Mystery solved. Now you might be thinking, okay, that's a clever solution, but this is all just super weird abstract theory. But this wave-particle duality isn't just some strange quirk. It's actually the fundamental reason that, well, anything exists at all. Have you ever wondered why atoms don't just collapse? If an electron was just a tiny classical particle orbiting a nucleus, it would constantly be radiating away energy, which would cause it to spiral inwards and crash into the nucleus. The entire universe of matter would be gone in a fraction of a second. But its wave nature saves it. The electron's wave has to fit neatly around the nucleus in a stable, standing pattern, which forces it into specific, fixed energy levels. It can't just spiral in, it has to jump. This duality is literally the bedrock of all of chemistry, all of matter. And this isn't just for tiny little electrons. This number you're seeing, 2.5 picometers, that's the measured wavelength of a buckyball, a huge molecule made of 60 carbon atoms. Even something that massive, on a quantum scale, has a measurable wave nature. This quantum weirdness is truly everywhere. And get this, you can actually see these wave principles in action for yourself. You can build a surprisingly accurate device to measure the width of a human hair using nothing more than a laser pointer. The hair acts as an obstacle, and the laser light, acting as a wave, diffracts around it, creating an interference pattern. By measuring that pattern, you can calculate the hair's width. It's basically a homemade quantum micrometer. So, case closed, right? The probability wave ties it all together in a neat little bow. Well, not quite. The quantum detective story has a modern twist that shows we're still arguing about some of the really deep parts of this mystery. You see, for decades, the law of the land was Niels Bohr's principle of complementarity. It basically says that the wave and particle sides of an object are mutually exclusive. You can set up an experiment to see its particle nature, like which slit it went through, or you can set up an experiment to see its wave nature, the interference pattern. But you can never, ever see both at the same time. Looking for one automatically destroys any information about the other. But then, some clever new experiments came along that seemed to break that sacred rule. This quote is from a research paper on something called the offshore experiment, and its claim is, to put it mildly, astonishing. It claims they saw both. Here's the basic idea. The experiment is designed to first confirm that a wave interference pattern exists. Check. Wave nature confirmed. But then, using a clever setup, it also claims to get reliable information about which path the particles took. Check. Particle nature confirmed. In the same experiment. This result seems to violate a fundamental mathematical limit based on complementarity, and to this day, the physics community is still fiercely debating what it all means. The story is far from over. And that leaves us right here, face to face with the deepest, spookiest question of all. The double-slit experiment proves, without a doubt, that the universe behaves differently depending on whether or not we're watching it. So that forces the ultimate question. What is the nature of reality when no one is looking? And that, right there, is the quantum riddle.